After studying this chapter, you should be able to do the following. Describe edge and screw dislocation motion from an atomic perspective. Describe how plastic deformation occurs by the motion of edge and screw dislocations in response to applied shear stresses. Define slip system and cite one example. Explain how grain boundaries impede dislocation motion and why a metal having smaller grains is stronger than one having large grains. Describe and explain solid solution strengthening for substitutional impurity atoms in terms of lattice-strain interactions with dislocations. Describe and explain the phenomena of strain hardening or cold working in terms of dislocations and strain field interactions. We learned from last chapter that above the yield strength, plastic deformation, which is the permanent deformation, will occur. But how? Well, from the atomic perspective, plastic deformation corresponds to the motion of large number of dislocations, or the dislocation motion. So let's see the relation between the plastic deformation and dislocation motion. So we're going to use examples for the edge involve edge dislocation, which is easier to see. Well, now we have an edge dislocation at plane A, and we are going to apply shear stress on this part of crystal arrangement. So shear stress means the stress is parallel to the plane. So we're talking about the horizontal planes. So now here is the shear stress. We have a pair of shear stresses. One is pushing the horizontal plane to the right, and another one is pushing the horizontal plane to the left. And this shear stress is perpendicular to the edge dislocation line. So here again at plane A we have an edge dislocation, and we know this edge dislocation line is into the screen or into the board. Therefore the shear stress is perpendicular to the edge dislocation. So when the shear stress is applied as indicated, plane A is forced to the right, and in turn pushes the top half planes of plane B, C, and D, and so on in the same direction, all to the right. If the applied shear stress is of sufficient magnitude, then the interatomic bonds of plane B will break along the shear plane, along this plane where the dislocation moves along, and the upper half of the plane B becomes the actual half plane as plane A links up with the bottom half of the plane B. So which means when it pushes, then the plane A will link with the lower half plane of plane B, where this plane B breaks over here. So B plane becomes the actual half plane, like this. And this process is subsequently repeated for the other planes. So this plane or the actual half plane keeps moving to the right, while this band keeps breaking and reform. So by such that the actual half plane by discrete steps moves from the left to right by successive and repeated breaking of the bounds and shifting by interatomic distances of upper half planes. So ultimately, this actual half plane may emerge from the right surface of the crystal, forming an edge that is one atomic distance wide, shown here, Well, this is the plastic deformation. For deformation to occur in a perfect single crystal, so perfect means there's no defects, no dislocations, then every bond connecting two planes would have to break at once in order to shear off a lattice plane. For example, if we want to break, then we need to break this row of bonds all at once, which requires a large amount of energy. However, due to dislocations in real materials, it is no longer necessary to break all bonds between two atomic planes at once. Rather, it is enough to overcome only one bonding series at a time. And the dislocation line jumps step by step from atomic row to atomic row with little effort and finally emerges as a slip step on the surface of the material. So the low energy sliding, we call this the movement the sliding of the atomic plane by a dislocation can be illustrated by moving our carpet. So moving a large and heavy carpet usually requires a very large force due to the friction between the carpet and the floor. If, however, wrinkles are stuck in the carpet and these are then moved through the carpet like this, then we can achieve the same result with less effort. So the carpet can move in stages like a caterpillar. We just mentioned that the carpet can move in stages like a caterpillar. Actually, dislocation motion is analogous to the mode of locomotion employed by a caterpillar. The caterpillar forms a hump near its end by pulling in its last pair of legs a unit leg distance. The hump is propelled forward by repeated lifting and shifting of leg pairs. So when the hump reaches the head of the caterpillar, the entire caterpillar has moved forward by the leg separation distance. So the caterpillar hump and its motion correspond to the actual half plane of atoms in the dislocation model of the plastic deformation. So the dislocation motion is resulted from the movement of actual half plane of atoms by breaking and reforming of interatomic bonds. But the dislocation motion is not termed as the carpet motion or caterpillar motion or caterpillar movement. Instead, we have a term for dislocation motion, which is slip. The process by which plastic deformation is produced by dislocation motion is termed slip. The macroscopic plastic deformation simply corresponds to permanent deformation that results from the movement of dislocations or slip in response to an applied shear stress. So if we have an edge dislocation, now this is the edge dislocation line over here, and if we apply shear stress to this lattice crystal or the crystal lattice, so the shear stress is parallel to the top and bottom surface of the lattice. Now you can see the dislocation at beginning, it's located inside this crystal. But as a result, it will move all the way to the right and move out of the surface to form this slip step. So that means the dislocation motion is in the same direction as the applied shear stress for edge dislocation. But if we have a screw dislocation, So this is the screw dislocation line, and now we can see we apply the same shear stress that is parallel to the top and bottom surface. As a result, this dislocation line will move backwards in this direction, showing in this arrow. That means the direction of screw dislocation line moves perpendicularly to the direction of the applied shear stress. But the net plastic deformation for the motion of both dislocation types is the same. Dislocations do not move with the same degree of ease on all crystallographic planes of atoms and in all crystallographic directions. Typically, there is a preferred plane, and in that plane, there are specific directions along which dislocation motion occurs. So we call this preferred plane the slip plane. Is the crystallographic plane on which slip occurs most easily. And usually this is the plane with high or with the highest planar density, which is the closed packed plane in the FCC structure and is the most close packed plane in the BCC structure, for example. And the crystallographic direction along which slip occurs most easily is the slip direction, and is the direction with the highest linear density, or it is the plane that is most, or this line that is most closely packed with atoms in the crystal structure. And a combination of the slip plane and slip direction is called the slip system. We learned earlier that in the FCC crystal structure, the closed packed plane is the 111 plane, and the closed packed direction is the 110 direction. So for the FCC crystal structure, the slip system is 111 plane plus the 110 direction. And there are a total of 12 independent slip systems for FCC. So here on each 111 plane, we have 3 different 110 directions. And now we have a total of 4 111 planes. So 4 times 3, we have 12 independent slip systems for FCC. Because of that, metals with FCC structure are quite ductile, because extensive plastic deformation is normally possible along the various systems. Again, the movement or the dislocation motion will result in the plastic deformation. The more slip systems present in the material, the more easier for the dislocation to move. Therefore, the material will be more ductile. For a single crystal specimen that is stressed in tension, deformation will appear as in this figure, where slip occurs along a number of equivalent and most favorably oriented planes, or the slip planes. Since it's a single crystal, which means we only have one big grain throughout the entire structure, the grain means all the planes or all the unit cells are in the same orientation. That's why those planes, the slip planes or closed packed planes, are parallel. So those slip deformation forms as small steps on the surface of the single crystal that are parallel to one another, and loop around the specimen as indicated in this figure. And each step results from the movement of a large number of dislocations along the same slip plane. And on the surface of a polished single crystal specimen, these steps appear as lines, look like this, which are called slip lines. Deformation and slip in polycrystalline material is somewhat more complex because of the random crystallographic orientations of numerous grains. The direction of slip varies from one grain to another. So on the application of stress, slip in each grain on most favorable slip systems, and again those systems have different orientations in different grains. Therefore, in this microscopic structure or microscopic graph, the slip lines in different grains have different orientations. By understanding the atomic mechanism of deformation and the central rule of dislocations, specific measures can now be taken to prevent deformation. After all, many materials that are used under high load should not deform so easily. So the reason why we learn the mechanism of deformation is to know how to make the metals stronger. Defects, especially dislocations, play an important role in controlling the mechanical properties of materials by interfering with slip and therefore strengthening the material. Because the ability of a metal to plastically deform depends on the ability of dislocations to move. The easier the dislocation motion, the more ductile or weaker the material is. Therefore, if we hinder or impede the dislocation motion, we will make the material stronger. And virtually all strengthening techniques rely on restricting or hindering dislocation motion. And for a metal to plastically deform, we know dislocations must move. And strength and hardness of the material is a measurement of the material's resistance to plastic deformation, which means they are related to the mobility of dislocations. If we reduce the dislocation mobility, that means the metal will be strengthened or hardens. And greater forces is necessary to cause the dislocation motion. Again, that means the materials is stronger. In the contrast, if we increase the dislocation's mobility, the metal will become weaker or softer or more ductile. So mechanisms for strengthening or hardening metals is to decrease the dislocation mobility. And we're going to learn 3 mechanisms to strengthen the materials, especially for single-phase metals. The first one is the grain size reduction. Second one, solid solution strengthening. And third one is strain hardening, which is also called cold working. The first strengthening mechanism is to reduce the grain size or grain size reduction, which is the process of strengthening the material by increasing the number of grains or reducing the grain size. The grain size or the grain boundary acts as a barrier to dislocation motion for 2 reasons. Let's take this 2 grains as the example. We have grain A and grain B. They have different orientations, and we have this dislocation. Well, move along the slip plane. First, at the boundary, because the two grains are of different orientations, a dislocation passing into grain B must change its direction of motion, and which is difficult compared to the crystal without the grain boundary. And second, the atomic disorder within a grain boundary region results in a discontinuity of the slip planes from one grain into another. So because of that, the grain boundaries act as barriers to dislocation motion. So by reducing the grain size, we will increase the grain boundary area, so there are more barriers to dislocation motion, which means it will hinder the dislocation motion. And by doing that, it will increase the yield strength and the tensile strength and the hardness of the material, which means the material is strengthened. A fine-grained material, which means the one that had small grains, is harder and stronger than one that is coarse-grained, because fine-grained material has a greater total grain boundary areas to impede dislocation motion. For many materials, the yield strength sigma y varies with grain size according to Hall-Patch equation, where sigma yield, the yield strength of the materials, equals to sigma 0 plus ky divided by square root of d, or times d to the power of negative 1 over 2, where sigma y is the yield strength, which is the minimum level of stress necessary to initiate plastic deformation, and d is the average diameter of the grains. Sigma 0 and ky both are constants or material properties. Grain size can be regulated by controlling the cooling rate during solidification from the liquid phase, and also by plastic deformation followed by an appropriate heat treatment, which we will learn later. So here is one example for grain size reduction strengthened brass alloy, and using this Hall-Patch equation and also from the measurement, we plot the grain size, or actually that's the reciprocal of the square root of d, which is 1 over square root of d, versus the yield strength sigma y. So it's a linear relation. So the yield strength of the brass alloy increases linearly with the 1 over square root of d. The second strengthening mechanism is the solid solution strengthening, which is the process of strengthening a material by intentionally introducing substitutional or interstitial atoms to distort the lattice and generate stress, which produce barriers to dislocation. This is like we're trying to move the carpet, but someone just placed a heavy steel ingot, for example, or put a chair onto this carpet, which will impede the movement of the carpet. Same idea, or which is analogous to this impurity atom, which will impede the motion of the dislocation by introducing the distortion to the surrounding lattice. So the principle of solid solution strengthening is based on the distortion of the lattice by foreign atoms. This can be either substitutional atoms or interstitial atoms. Due to their blocking of the dislocation movement, the lattice planes can consequently no longer slide off so easily. And a deformation of the lattice thus occurs only at slightly higher critical shear stresses, since the lattice distortion must also be overcome. In this way, an increase in the strength of the material is ultimately achieved. Please check YD Plus in Module Chapter 7 under 7.9 Solid Solution Strengthening, and then click onto this animation, which is an animation to explain solid solution strengthening mechanism in great details. This figure shows the effects of several alloying elements on the yield strength of copper. Pure copper has a yield strength of 10,000 psi. By adding different alloy elements, we can first compare across different alloys to see the effect. And also, we see that with increasing percent alloying elements, for example, aluminum, by adding more aluminum, the yield strength of the copper-aluminum alloy increases linearly. Same idea for different other alloying elements. But between different alloying elements, we can see the effects are different as well. And from this result, we can say that increasing both atomic size differences and amount of alloying element increases solid solution strengthening, which means the bigger the atomic size differences, the higher strength of the alloy. And the more alloying elements we add in, the higher strength of the alloy. By changing the nickel contents in the copper-nickel alloys, the mechanical properties of the copper-nickel alloys are changed as well. So it shows that with increasing nickel content, the tensile strength of the alloy increases. So that's the yield strength, which increases with the nickel content as well. However, the percentage elongation, which represents the ductility of the alloy, decreases with the alloying elements, which means solid solution strengthening increases tensile and yield strength but sacrifices the ductility. It decreases the ductility of the material. You may have the experience that if you bend a paper clip or a piece of copper wire, bend it back and forth. At the beginning, it might be very easy for you to bend back and forth, but after a couple of times, it becomes more hard or harder and harder to bend the piece of metal over. So this is one example of the strain hardening or cold work. So the principle of work hardening or strain hardening is based on the introduction of additional dislocations during plastic deformation. In every deformation process, new dislocations are always introduced into the material. The dislocations will hinder each other from moving, which results in a strength increasing effect. So this is analogous to creating, if we create more wrinkles in this carpet in different orientations, right? And now it will be more difficult for us to move the carpet on this floor. So with work hardening, additional introduced dislocations block each other from moving. The reason why string hardening is also called cold work because the deformation process happens at room temperature. And the common forming operations including cold forging, rolling, drawing, which will decrease the cross-sectional area, and cold extrusion. So all of those forming operations involve the change in the cross-sectional area from A0 to AD. So the extent of string hardening is therefore described by the percent cold work. Percent CW stands for cold work, which is the change in cross-sectional area over the original cross-sectional area times 100. In this diagram, we have the stress and strain curve of a low carbon steel after different percent cold work. So this green line is without cold work, blue line is 4% cold work, and the red line is 24% cold work. So after comparing the stress and strain curve, here is our conclusion. As percent C cold work increases, the yield strength increases. The tensile strength also increases, but the ductility in terms of percentage of elongation or percentage of area reduction decreases, which means, again, string hardening will increase the yield strength and tensile strength, but will decrease the ductility of the material. Let's use one example to check the effect of cold work on mechanical properties of, in this case, a cylindrical copper specimen. Compute the yield and tensile strengths and ductility for a cylindrical copper specimen that has been cold worked by reducing its diameter from 15.2 mm to 12.2 mm. So D sub 0 is 15.2 and D after cold work is 12.2 mm. And we're looking for the yield, tensile, and ductility for this copper specimen. We have a diagram which relates the percentage cold work to different mechanical properties. So we're going to check the graph to read off the values for tensile, for yield strengths, and also the ductility of the material. So the first step is to calculate the percent of cold work, which is the change in cross-sectional area over the original cross-sectional area. So now it's expressed in terms of the cross-sectional area, D0 and DD. We can cancel the pi out and also the 2 out and simplify the equation, which becomes an expression of D0 and DD only. And D0 and DD both are given. We can substitute the values and the percent cold work is 35.6%. Next, the mechanical properties of the copper can be determined graphically from the percentage cold work versus yield strength, tensile strength, and ductility plot. So we know that percentage cold work is 35.6, and we can find the corresponding yield strength, which is about 300 megapascal. Same idea for the tensile strength. It's approximately 340 megapascal, and for the ductility at 35.6%, it's about 7% of percentage elongation. In summary, dislocations are line defects that move and cause a metallic material to deform when a force is applied. The dislocation moves in a slip system, which is composed of a slip plane and a slip direction. The slip direction is typically a close packed direction, or if there's no close packed direction in the material, it will be the most close packed direction in that crystal structure. The slip plane is also typically close packed or nearly close packed plane. In metallic crystals, the number and type of slip systems influences the metal's properties. For FCC metals, it has an optimal number of slip planes, which causes FCC metals to be ductile. We know there are 12 slip systems in the FCC metal. Therefore, FCC metals are the most ductile, has the highest ductility. For BCC metals, it doesn't have any close packed planes, which causes the BCC metals to be strong and brittle. Although it has a lot of slip systems, but also if you have too much, the slip systems can interact with each other or hinder with each other to reduce the ductility or to reduce the dislocation motion. Therefore, BCC metals are strong and brittle, not as ductile as FCC material. FCC or HCP metals have a limited number of slip systems, which tends to make them more brittle. We learned 3 strengthening mechanisms: grain size reduction, solid solution strengthening, and strain hardening. All 3 strengthening mechanisms are based on the same concept, which is to decrease dislocation mobility. For grain size reduction, we increases the grain boundary areas. By decreasing the grain size, the grain boundary will hinder or impede the dislocation motion. For solid solution strengthening, we introduce impurity atoms, which will cause distortion to the lattice structure, which will in turn hinder or impede the dislocation motion. Strain hardening is to increase the dislocation density, and dislocation will interact or will stop each other from moving, therefore to decrease the dislocation mobility and to increase the strength of the material.